Dr. Commitment, Dr. Chairman, Dr. Krenovich, Dr. Cabrera. Thank you for being here. Thank you for accepting the invitation. Dr. Maristal. Thank you. Okay, let's start with this very parenthesis before I start. I start every chapter of my dissertation with a quote. So regarding what I'm going to talk in the chapter. So I'm going to start my presentation in the same way. I'm going to quote Steven Spielberg, which is people have forgotten how to tell a history. History do not have a middle or an end anymore. They usually have a beginning that never stops beginning. So why I'm going to start with that? Because I am going to perform my presentation in what is called the three-act structure. So the first act is going to be the setup, and here I'm going to present the introduction of the problem. What is the problem? I'm going to talk in the setup. I'm going to do the prerequisites. Reduce the modeling. I'm going to talk about the interval constraint solving technique. It's not my contribution, but it's very important to know that in order to understand the rest of the text. The act number 2, which is the confrontation, I'm going to talk about my contribution. I have contribution in the reduce the modeling, in prediction, parameter computation, and finite element method. And finally, what is going to be the resolution, which is the actress, is going to be the conclusion, and we are going to see if the story has a sequel, which means the future one. The spoiler alert is going to be. Act 1. Okay, what is the problem that we are? So, given a natural phenomenon, so we want to represent that in a mathematical model in order to make decisions. What kind of decision? Well, first we need to understand how dynamic phenomena unfold under different inputs. Different inputs here is going to have different outputs here. It's important to know right now that we cannot see the differential equation here. Why? Because sometimes you don't know what is the differential. You don't know what is the mathematical model. What you have is a black box. You have input here and you have output here. And so, every different inputs here, you have output. That is what we call understanding how to unfold depending on the parameters here, and that is what we work with simulation. The another thing is predicting. What does that mean in that case? Well, we have a phenomenon. We don't know, we assume that we don't know the parameter, we don't know anything about the phenomenon, but we have some observation. In that case, this is the representation of double pendulum, which is this is one position, the first one and the second mass, the second and the third mass, and this is the position of theta 1 and theta 2. And theta 1 and theta 2 are the angle with respect to the vertical of the here. So we have three observations. What we want is to know what the parameters take this position here and what is going to be the future of this model. Well, what we want to do is this. Now, depending on this, we have these parameters, and this we can recompute. Look, in this trajectory, it's very easy to predict, but this is very good. This is not chaos, actually. This is something because we know the formula. And the third is enforcing some behavior. Imagine you have a phenomenon, in this case, represented by this helicopter here. This helicopter has a nice trajectory, but for some reason, some unexpected situation happened. And if this helicopter resumes the movement using exactly the same parameter, something bad is going to happen because he's not going to land in the position when he's supposed to land here. So what the computer does, or what we expect to do, is you recompute the parameters here. You want to reach here from a new position here, and you recompute here the new parameter. In this case, this is a paper example. Don't think that is a very huge. This is a paper example. The only thing you have to recompute the position, the initial the value right now, the velocity, and you want to reach here, so recompute this, and then you read it. Okay, that is the problem we want to address. What is the challenge? But this problem has challenge. Okay, the first one is the size. When we have a differential equation, when we have a system differential equation, it doesn't matter if it's linear or not. One way to solve this is discretize the domain, and then we solve this, and we can solve it using linear system, using nonlinear system, Newton, whatever method you want to do. But what is true, is when you have, if the more accuracy you want, the larger is going to be the system equation. So that is going to be the first challenge. The second challenge is uncertainty. We are surrounded by uncertainty because the algorithm measurement instrument, because the computer, because we are taking decision, or we are assuming something that is not true, and we are surrounded by uncertainty. We have to handle that. For example, this is an example. The weight of a body or some object is the multiplication, is the product, or the mass of the object by the gravity. In this case, this, right? Are we sure? Are we sure? Because look, the gravity depends on the way you are standing on. If you are standing in the pole, the gravity is going to be higher than if you are standing in the equator, which means that is not 100%. So uncertainty is another challenge we have. And another one is the reliability. When we are doing simulation, it's not only to get the data. We have to be sure we can trust in that data. So that is what I mean. For example, this is a classical example in order to exemplify this situation. Imagine you have this expression here, and with the A is this value here and B is this value here. When we evaluate using 128 bits, we obtain this value. It's 128 bits. It's more than double precision. So we can trust on that. Actually, we cannot. Because the correct answer is this. Not even the sign is the same. Not even the magnitude. So we cannot trust it. That is a classical example of people who work in the computer, in the interval computation. Another not so classic is given by Dr. Stephen Robinson in his article Force Numerical Convergence on Generalized Newton Method. Newton method is very good, is the quadratic convergence, but when you take an initial condition very close to the solution. But sometimes Newton method doesn't converge because it's in infinite cycle. That is bad, but not so bad. Because if Newton method doesn't converge, you say, well, it doesn't converge. But what is bad, and really bad, is that Newton method converges. One believes that is the solution, and actually it's not. So that is an example that we, Dr. Robinson, try to exemplify that case exists. Okay, we have the problem. Now, how we address this challenge? Well, for the size, we reduce the problem. We reduce the problem using reducer. Very small parenthesis here is this is a cat. And I know many people who love cats, right? But you cannot take this cat. But probably this. So, this cat, you reduce the problem, now you can handle the problem. So, you like the cat, you like the lion, cat, reduce it, now you can handle it. You can take this one. And you put a very small, and this guy, you really want to handle. So that is what we call reduce-order modeling. That is not the model. The reduce-order model is the process to take a big problem to reduce it to one smaller, and then you solve this. Okay, this is a model to which we handle this using reduce-order modeling. Okay, remember, I'm going to go moving forward and backward depending on what the position. Okay, if you working here, we were wrong because this is not the exact position of the gravity. Actually, the gravity moves in a range, and that is how we are going to handle uncertainty. I am not saying that is the only one way to do it. That is how I did in my presentation, and we have done in the research. We handle uncertainty using interval. This is the lowest one is given in the Nevada Volcano mountain in Peru, and this is the highest one in the article share because it's and the reliability. Many ways to handle reliability. What we do is, for example, using our outward routing, which means this example is very good. 0.1 is a number which is not representable by a computer number. So we represent this number by a closed interval, and what we do is now representing the lowest here and the lower bound and upper bound. What you have is now you have an interval, this is a number. And every operation you do is going to be rounding outward. So you know that in every operation you always going to be enclosing the resolution. Probably its width is very wide, but you're not completely sure that that is the solution you are looking for. And another thing is very good with using that is, for any reason, the system, the method that you are using return that there is no solution, you are completely sure that there is no solution. So it's not because it's not able to be. So using interval, okay. This is the problem. This is what are the challenges and how do we handle the challenge. We have to be more specific in any of them. How we can pass from this line to do it pretty key. Okay, reducer the modeling is no more than this. We have a function from Rn to Rn. We are looking for the zeros of the function, which is this. We know that for any reason that the function is in one affine space. This is the red one in the solution we are looking for, which is this red one here. And the projection is the green part here, and this is the different orthogonal projection here. If our way how to get the reducer of the model is very good, this blue part is going to be close to zero, which means we, in any case, imagine zero, we are solving this problem here. We have to solve this. So what we transform this lion here, which is a very large vector in the dimension n, to the very kitty here, which is a very small dimension. Remember, imagine this is. So reducer the modeling is looking for this figure in the basic document. Depending what method you use, always is going to get the basic, because all you are going to get the subspace of this subpage.